Chapter 1.8.10 Multi-tenancy. This text provides guidance on cluster multi-tenancy by sharing clusters to save costs and simplify administration. Challenges like security, fairness, and managing noisy neighbors arise when sharing clusters. Various ways of sharing clusters are discussed, whether running different applications or multiple instances of the same application for different end users. Kubernetes offers features to manage different tenancy requirements. Use cases. Multi-tenancy in Kubernetes clusters can take on two main forms: sharing a cluster between multiple teams within an organization, or running multiple instances of a workload for customers as a software-as-a-service SaaS vendor. In the first scenario, teams operate their own workloads and often need to communicate with each other. Members have access to Kubernetes resources directly or through automation tools, with trust playing a role in sharing. Policies like RBAC, quotas, and network policies are crucial for secure and fair allocation of resources. In the second scenario, customers do not have access to the cluster, and the vendor manages the workloads. Cost optimization is a key concern, and strong isolation between workloads is achieved using Kubernetes policies. Both forms of multi-tenancy require careful consideration of the use case, patterns, and tools available to effectively share clusters. In Kubernetes, the concept of a tenant can vary depending on whether multi-team or multi-customer tenancy is being discussed. In a multi-team model, a tenant is typically a team that deploys workloads that scale with the complexity of the service. On the other hand, in a multi-customer model, a tenant is a group of users who share a single workload. Organizations may use both definitions of tenants in different contexts. There are different ways to design and build multi-tenant solutions with Kubernetes, each with trade-offs that affect isolation level, implementation effort, operational complexity, and cost. Tenant isolation can be applied in both the control plane and the data plane of a Kubernetes cluster to meet organizational requirements. Hard multi-tenancy implies strong isolation, often used when tenants do not trust each other from security and resource-sharing perspectives. On the other hand, soft multi-tenancy implies weaker isolation. Isolation techniques must be applied to both the data plane and the control plane. In some cases, it may be necessary to assign each tenant their dedicated cluster for stronger isolation, especially if security concerns are high. The multi-cluster SIG is responsible for addressing use cases where dedicated clusters may be necessary. Even if considering dedicated clusters, it may be valuable to review isolation techniques for shared Kubernetes clusters for flexibility in the future. Each organization must evaluate the benefits of stronger tenant isolation against the complexities of managing multiple clusters. Control plane isolation. Control plane isolation in Kubernetes ensures that different tenants cannot access or affect each other's API resources. Namespaces provide a way to isolate groups of API resources within a single cluster, allowing for overlaps in object names across namespaces. Many security policies in Kubernetes are scoped to namespaces, such as RBAC roles and network policies. RBAC can be used to restrict access to namespaces and ensure the principle of least privilege is followed. Access controls are crucial for maintaining isolation within the control plane. Authorization through RBAC is commonly used to restrict access for users and workloads at the namespace level. Role bindings are used to enforce access control at the namespace level, while also ensuring that privileged users have access to cluster-wide resources. Quotas can be used to manage resource usage of tenant workloads. limiting the number of API resources a tenant can create to prevent resource monopolization and noisy neighbor issues. Quotas, when applied to namespaces, ensure that tenants consume resources within their allocated share. Resource requests and limits for each container must be specified to prevent containers from consuming resources beyond the configured limits. Quotas do not protect against all types of resource sharing, such as network traffic, which may require node isolation as a better solution. Overall, proper configuration of namespaces, access controls, and quotas, along with adherence to security best practices, are essential for ensuring control plane isolation and resource management in a multi-tenant Kubernetes environment. Namespace management tools can help simplify administration and enforcement of these policies, allowing for flexibility and scalability in a multi-team environment. Data plane isolation. Data plane isolation is important for ensuring that pods and workloads for different tenants are sufficiently separated to prevent security vulnerabilities. By default, all pods in a Kubernetes cluster can communicate with each other, leading to potential risks of traffic interception or redirection. Network policies can be used to control pod-to-pod communication by restricting it based on namespace labels or IP address ranges. In a multi-tenant environment, starting with a default policy that denies communication between pods and allows DNS queries for name resolution is recommended. More permissive rules can then be added for communication within a namespace. It is advised not to use empty label selectors for namespace fields in network policy definitions to allow traffic between namespaces if necessary. Namespace management tools can simplify the creation of network policies and ensure consistent namespace labels throughout the cluster. For storage isolation, Kubernetes offers different types of volumes for persistent storage. Dynamic volume provisioning is recommended for security and data isolation, and volume types that use node resources should be avoided. Storage classes allow administrators to define custom classes of storage based on various criteria. Persistent volume claims enable isolating portions of the storage system for specific tenants within a shared cluster. It is important to note that persistent volumes are cluster-wide resources with independent life cycles. Creating individual storage classes for each tenant can enhance isolation, and setting a reclaim policy of delete for shared storage classes ensures resources are not reused across different namespaces. Sandboxing containers is essential for isolating workloads running on shared clusters to protect against potential vulnerabilities and exploit threats. Sandboxing involves running each pod in a separate execution environment, such as a virtual machine or user space kernel. This is particularly recommended when running untrusted code and helps prevent container escapes, where attackers exploit vulnerabilities to gain access to host systems. Popular sandboxing implementations include gvisor and Kata containers, offering secure container runtimes with added layers of security. Node isolation is another effective technique for isolating tenant workloads by dedicating specific nodes to running pods for a particular tenant. This reduces the risk of noisy neighbor issues and limits information disclosure in case of container escapes. It is important to note that while workloads from different tenants run on separate nodes, shared services like kubelet and API service are still vulnerable to skilled attackers. Compensating controls such as seccomp, AppArmor, or clinux can be implemented to enhance security. Node isolation simplifies billing and can be implemented using pod node selectors or a virtual kubelet. It offers easier manageability and compatibility compared to sandboxing containers. Additional considerations. The text discusses various Kubernetes constructs and patterns that are relevant for multi-tenancy in SaaS environments. One key feature is API priority and fairness, which allows assigning priorities to pods for different applications. Quality of service QoS tiers can be offered to different tenants using network QoS, storage classes, and pod priority and preemption. Networking QoS, for example, ensures fair bandwidth allocation among pods. Storage QoS involves creating different storage classes with varying performance characteristics. Pod priority and preemption can be used to assign priority values to pods and schedule them accordingly. Additionally, DNS services in Kubernetes clusters can be configured to restrict cross-namespace lookups for stronger isolation in multi-tenant environments. Operators are Kubernetes controllers that manage applications and are commonly used in multi-tenant environments to simplify the management of multiple instances of an application, ensuring resource requests and limits are configured for fair scheduling and to support data plane isolation techniques. Overall, these constructs and patterns help in providing quality services to tenants, managing applications efficiently, and ensuring fairness and isolation in a multi-tenant SaaS environment. Implementations. The text discusses two primary ways to share a Kubernetes cluster for multi-tenancy, using namespaces or virtualizing the control plane per tenant. Namespace isolation is well supported by Kubernetes, but may be difficult to configure and does not apply to all Kubernetes resources. Control plane virtualization allows for isolation of non-namespaced resources, but comes with higher resource usage. Using a namespace per tenant is recommended for workload isolation, while virtual control planes provide complete control over cluster-wide resources. The text also mentions the hierarchical namespace controller, HNC, for organizing namespaces into hierarchies, as well as projects like Capsule, Kubeplus, Kyverno, and OPA Gatekeeper that aid in managing namespaced resources. Virtual control planes provide improved isolation but come at the cost of running and maintaining individual control planes per tenant. The Cluster API, Nested Kton project provides an implementation of virtual control planes, and other implementations like Kamaji and vCluster are also mentioned.